this video is with reference to l8v2 and l8v4. l8v2 is for open loop, l8v4 is for closed loop. So in this video we're going to compare both of them and somewhat to show you the differences between their certain modeling system. For the open loop system, we have actually shown you for in l8v2 that the error, alright, the estimated state error over here can be represented as AX curly bar. Alright, so I'll just simply paste it over here. Alright, as for the closed loop, which is the previous video, we actually show you that the estimated state error is A minus LC. Okay, so I'll just paste it over here also. Okay, so therefore what are the differences between them then? For both systems, you want your error, your estimated state error to be 0, right? So that your real system will be equals to your model system, or I should say that your model system, because you want to model the real system, so your model eventually becomes your real system. Okay, when this happens, your estimated state error should be 0, which is this one, and this one should be all 0. Okay, so I'll just write it down. Okay, so both of them are equals to 0 already. So what is the thing that we're going to do next? For open loop system, okay, your eigenvalue of A, okay, sorry, your state, your system state, alright, will always be in terms of the eigenvalue of A, because we know that the S curly bar for both of this case should not be 0, because to some extent, to a more realistic extent, they can't be 0. Alright, so in order for this thing to be 0, alright, your A has to be 0. I mean, your A matrix has to have certain eigenvalues such that this thing becomes 0. Okay, so the eigenvalue of A in such of a case, if it's because it's all constrained by the eigenvalue of A, so therefore the value of the eigenvalues of A, for example, if it's small, which is minus 0.1 or minus 0.3, if you have a two-state, meaning you have x curly 1 and x curly 2, you have a two-state system, for example, okay, then your output is somewhat very slow. If it's minus 100 and minus 300, alright, if your eigenvalues for let's say the next value of A, or for the next matrix of A with other in other words, for different matrices of A, you may output another set of eigenvalues, okay, which in this case the responses is pretty fast. Alright, this is slow, this is fast. We have proved to you in l8v2 of the video. Alright, but the purpose of me taking in this thing for you to see is that we want to build on this thing, because everything is constrained by A. Alright, your A, where does this A come from? This A comes from this A over here. Alright, your AX plus BU, if you still remember. Okay, or in other words, the more better one, this one. Alright, this is all coming from A, and this A, B, C comes from where? Comes from a certain transfer function. Alright, ys over u of s, and then somewhat you change it to a state space using this thing. Alright, and you have a certain matrices for A, B, C. Alright, this is being proved all the way back from video l8v5 if you were to watch that video. Okay, so by knowing this matrix A, and we know that we are only constrained by the output only constrained by the matrix A, alright, in open loop system, and we cannot change anything at all. Alright, we can only see that it is slow. Alright, and then if we were to change our transfer function and we plot again, we may actually have something more faster, but it's not something as we want. So you need to constantly update your open loop system, which is not cool, right? So you want a closed loop system to update your system automatically, alright, and somewhat also to shift to whatever speed that you want, alright. Because for example, if you want to adjust it to medium fast, alright, this is medium fast, alright, compared to slow and fast, this is somewhat medium fast. In order to do that with a closed loop system, you can easily do that by adjusting your gain L. Alright, and now this is certain matrices. Alright, you will have L2, L1, etc. Later on we'll deal with this. but I just want to inform you that you can adjust your L such that you can control or adjust the whole system to whatever output that you want. Okay, so the powerful impact of the closed loop system is this: you can adjust the speed that you want based on controlling your L. Alright, where L comes from your closed loop pulse, your desired closed loop pulse. Alright, and you may wonder what is C. The C is the same thing. A certain transfer function y of s over u of s, and then you sum up plot in terms of a state space. You have A, B, and C, right? So this C is a matrix that comes from your transfer function, where a transfer function is an open loop system. Alright, your open loop system, if you have a certain in its own poles over here, okay, as maybe like s squared, for example, the transfer function may be equals to 2s squared plus 7s plus 12, right? So this thing over here is your open loop poles, and eventually if you want to shift it such that your closed loop poles will have something like this, maybe ATS plus 1100. Alright, so your overall poles will increase, and therefore you have a higher speed that you want. Alright, things like that. And therefore, in order to do that, the open loop system offer no help. Alright, only the closed loop. And therefore, we should be using this one. Okay, and in such of the case that happens, we're going to use an example to prove to you, or not prove to you, but rather than show you how the L is being applied. Alright, and how the A and C all comes about. Okay, so then for this is it, and I shall see you soon in other stuff. I mean in the next video for example to prove to you this thing. Okay, see you.